right. Okay, good afternoon. This is the last lecture before you make your oral presentations of the term paper, which will take place on Tuesday, next Tuesday, right? And you know, if wonder, since this is the lecture, maybe I'll ask you whether there are some topics that you think we should discuss, but we did not discuss. Why don't we start with that? And if you see some topics there, maybe we'll spend time on that. What I did bring here today, of course, are the slides you have. That is some continuation with the bipolar discussion we started last time, right? We have a continuation of that. So is there any topics perhaps related to the CMOS, or at least somewhat related to the CMOS device or technology that you would like to have some discussion in this hour? Any questions? Suggestions? No? All right, let's continue with this bipolar transistor discussion, all right? What did we do last time? Last time, actually, we did look at a cross-section of advanced bipolar transistors, and we also showed you the Venn diagram of a silicon germanium bipolar transistors. I think it's useful to know that silicon germanium bipolar transistors creates a built-in field by using a wider bandgap semiconductor near the emitter and narrower bandgap semiconductor near the collector. So here, actually, basically, it's all silicon. That's the way it's done right now. At this point, maybe a silicon is 0.9 or 0.85. Actually, 10% is about all that takes. And germanium is 0.1. All right? Just with this gradient, you more or less linear gradient, you end up with a slope in the conduction band edge, and that is an electric field. Any electron that's in the conduction band will just pushed away toward the collector, or drift toward the collector, and this gives silicon germanium superior speed. All right. Most of the time we spent last time had to do with base widening or Kirk effect. And the important thing about this phenomena is that limits the maximum speed of the bipolar transistor. If it's not for that reason, in principle, we can push the frequency to much higher. But because the base gets wider when the current density is very large, speeds start to decrease at a high current density. So as a result, the transistor speed increases with increasing current and peaks at some point and drops. Whereas it peaks is somewhat a function of, not that strong a function of VCC, all right? The voltage or bias voltage between the collector and the emitter, somewhat. Okay? Any questions about what we talked about last time? All right? Not. There are a few little things here we're going to talk about. First is something called heavy doping effects or band gap narrowing effect. You may remember that I made a comment last time that the classical way of creating a built-in field by doping the base more heavily on the emitter side and less heavily on the drain side of the base is somewhat mitigated by this effect. All right. But however, this term usually refers to the emitter. In the emitter, because doping is so heavy, we end up have a band gap narrowing, which results in a reduction in the current gain, beta. And let's see what happens here, all right? Now, the perhaps I would not, how do I do this, all right? Okay. All right. All right, maybe I wouldn't, maybe this thing actually is better if we do this later on, perhaps. Let me think if I do this a little. All right, maybe it's actually, yeah, perhaps, excuse me, stored charge. Okay. Well, I guess won't help. If we delay this till the next topic, probably will not help. Therefore, let me just go on and talk about it. All right. So I'm going to just I guess tell you that it can be shown that in order to have a good current gain, we have to have a large emitter efficiency. Emitter efficiency is defined this way. That is, when we forward bias base and emitter junction, when we forward bias the base and emitter junction, all right, base emitter junction, some electrons will be injected from emitter into the base, and some holes will be injected from the base into the emitter. Is that right? Okay. The ratio of those two currents, the electron current to the total current, all right, I guess it's not the ratio of those two. The ratio of the electron current to the sum of the two, which is the total, is known as emitter efficiency. The emitter efficiency should be very close to 1 if we want to have a good high gain transistor. Let me rephrase that. Another way to rephrase this is look at the ratio between the emitter, the electron current and the hole current. As I said, there are two components of current. One's electron current that's injected from emitter into the base. That's the good current, because those electrons then later would diffuse or drift through the base and become our collector current. So this is the good current. We want that to be large, all right? But any time when this p-n junction is forward biased, some holes will be injected from the base into the emitter. That's what we call hole current. Hole current is the bad current. It's undesirable side effect of the forward biasing of the emitter-base junction. Why is undesirable? Because turns out most of the base current we have to supply is used to supply this hole current injection into the emitter. Therefore, if we can make this ratio very large, we can get a very large collector current to base current ratio. We get large current gain. Do you follow this? So this basically is the base current, and this basically is the collector current, roughly speaking. So we really want a lot of carrier injection from emitter into the base, very few carrier injection from base into the emitter. All right, that's a fact. Second fact, it can be shown that when you have a p-n junction, the ratio at any forward bias, the ratio of those two component current is equal to this ratio. Okay, first let's not look at this NIE part. It's equal to NE over NB. So you want to dope the emitter heavily and dope the base lightly. If you do that, then you get a large electron to hole current ratio. All right? That's fine. That's the first order, so we certainly should remember that. We want to dope the emitter more heavily, dope the base less heavily. Okay? We cannot dope the base lightly because we need to reduce the base resistance, the sheet row. We want to make the base sheet row very low, and base already very thin, so we have to dope the base reasonably heavily, right? We want to push this close to 10 to the 18th. So as a result, we really have to dope the emitter very heavily, 10 to the 20th and above. Now, unfortunately, when you dope the semiconductor so heavily, it's known that the band gap narrows, right? All right. Because the band gap narrows, then the intrinsic carrier concentration becomes smaller, because intrinsic carrier concentration squared is equal to NC times NV exponential minus EG over KT. You may remember that. These two quantities actually also change. In fact, we just lump all the effect into EG. Basically, what that means is when the doping concentration is large, Ni drops. All right, so that's what happens. So Ni increases. This lowercase Ni increases when doping concentration is large, right? When dopant is large. Okay, how large is large? At 10 to the 18th, we begin to see this effect. At the 10 to the 20th, it's very strong, so strong that it's really going to cause us a big problem that I'll describe right now. All right? Okay. Now, if Ni squared is not a constant, that Ni square actually depends on the dopant, it can be shown that the ratio of these two components current in a p-n junction is not simply the ratio of the dopant concentrations, but rather the ratio of the dopant concentration over the Ni square on one side of the p-n junction to the dopant concentration over Ni square on the other side of p-n junction. All right? So I would not go through derivation with you. If you look at derivation of the p-n junction theory, you will find this is it. We just did usually omit this because they are often assumed to be equal. All right? But if they are not equal, we'll have that thing. Now, the trend, unfortunately, is when doping concentration is large, NIE increases like this, roughly speaking. All right? Okay, starting at 10 to the 7 18ths, we'll start to see this and rises. And below 10 to the 18ths, pretty much constants. We don't have to worry about that. So as a result, even though if we use, say, 10 to the 19th here, 10 to the 21st there, we don't get 100 of current gain. We'll be lucky if we get 10. In fact, we won't get even 10 because the difference of NIE square is more than a factor of 10. You see that? Okay. So this is known as the heavy doping effect. It's also known as band gap narrowing. In other words, it's very difficult to design a transistor with high gain just simply by choosing the dopant concentrations in emitter and base. Is that right? Okay. So what can you do? Well, there are several things one does, but because there's one very good thing, I won't mention any other things that when try to minimize this effect. It's the thing is, don't use silicon in the emitter and in the base. For example, we do use silicon in the emitter and accept the fact that band gap is going to be a little smaller as because heavy doping, right? We choose another material for the base whose band gap is even smaller. Hence, silicon germanium. Is that right? Okay. So silicon germanium actually has two benefits. One is solve this heavy doping problem. Two is give us a drift field. It actually does two things. All right? Can you think of a way to use silicon germanium to only solve the heavy doping effect without introducing a drift field? Can you see a way to do that? Uniform germanium concentration, exactly, right? We have uniform germanium concentration. It definitely still gives us a lower band gap, solve this problem. The DC gain is good, but there will be no drift field so that the cutoff frequency would not be very high, okay? Both are important. We want good current gain. We also want high cutoff frequency. And in fact, cutoff frequency probably is even more important than gain, but both are important. All right? So by using graded doping, silicon germanium, we manage to solve both problems. All right? Okay, good. So with that, and I'll just go away from this. And yes? So question, Turi? Yeah.
Why, in practice, do the silicon germanium devices not really have a lot higher beta? It seems like the devices that are actually in the fields, have they traded off another thing?
This is what I mean. By beta does not necessarily give us that much gain. I mean, by having a higher FT, you can sell it for a lot more. By having a little more beta, you cannot sell it for a lot more. So you have to think, gee, if I don't go all for that beta, can I gain something else back? All right? And you, as a designer, I think you realize this. If the gain is very poor, let's say the 2, nobody can use it for anything. So you have to try very hard to get that gain high. But once the gain is up to a point where it's pretty good, making it even higher doesn't buy you that much. You would rather than not push it higher, but use that freedom to make the cutoff frequency higher. For example, what are the things to trade off between the gain and the cutoff frequency? If I wanted to push the gain of silicon germanium transistor higher, I'll simply use a lower dopant concentration in the base. You see that? But that's going to introduce seed resistance in the base and kill my cutoff frequency. So what do I like better? So it's usually this kind of trade-off. I just want good enough gain and everything else is thrown into speed. That's why you don't see significantly better. So then you ask, why were we able to get that kind of gain without a silicon germanium? Well, because if we didn't get that kind of gain, we just have even other problems, so we just sacrifice what I can get in the speed and get the gain there, right?
And in practice, it also seems like the variability in beta is a lot higher in silicon germanium. Is there a reason for that?
That's very interesting. I did not know that information. That's a very interesting piece of information. I can certainly see one reason. I'm just conjuring up. Anytime you have additional variable in the process, additional number of variable in the process, you expect a larger range of variation in the device characteristics. So in this case, certainly the silicon germanium concentration is a variable now, right? And so that will be easy way to guess. That's probably what it is. All right. It's not easy. We're talking about 800 angstrom thick film whose composition is changing linearly from one to the other, and all this being done by epitaxial growth. And it's certainly not something easy to do. All right? Okay. And, okay, great. Anything else? All right. So let's move on to another topic. This topic is, we say it's an arbitrary doping profile, but actually the analysis can be easily extended to changing band gap, such as silicon germanium concentration. So what really is arbitrary building field, all right? Okay, but this lecture notes was prepared, I guess, a couple of years ago. I didn't think of updating it at this time. So let's still follow this through. Maybe if you're interested in this, see how you can change the interpretation of some terms and make this apply to changing a band gap, all right? Okay. So the question is, suppose I have built-in field, and then how can we develop some theory about the transistor? And to begin with, it appears we're going to develop a theory for beta. Actually, we won't even get there. We eventually will come up even with speed. We'll see what we're talking about, all right? The charge storage, transit time. We'll see how this come about. So think that there's a built-in field. Maybe it's a result of changing the doping profile. But maybe we'll point out somewhere it actually does apply when we have a varying band gap. So the first thing is we decide that we're going to use a simple NPN transistor. I don't know why this plus is there. Certainly there's no intention to say the collector is N plus, all right? Just NPN, all right? Okay? Make assumption that beta is very good. Therefore, there's really no whole current flowing in the base. We're treating a one-dimensional problem. Just thinking about electron flowing across the base is what we're going to be treating, all right? And we're going to make a simple assumption that there's no whole flow, at least not in this particular dimension, not in this direction. There's no whole flow, all right? Now, the whole current density, therefore, we can say is 0 because we say there's no whole current flowing in the base, all right? Okay, at least in the direction between source and drain, this direction. And the whole current density is equal to QP mu PE minus Q dP dP dx. You see that? There's the drift term and the diffusion term, right? We're not saying we know what E is. E can be anything, all right? Okay, you have some built-in field, can be anything, all right? Okay, does not even have to be uniform function of the, does not have the uniform across the base, by the way. Just any E, all right? At any point, then at any point in this x direction between 0 and W, in any point in this x direction between 0 and W, this relationship satisfied. That is 0 equal to Q P mu PE minus Q dP dP dx. The drift balances out the diffusion. So this gives us a handle on the electric field. Electric field must be equal to dP over mu P 1 over P dP dx. Okay? It doesn't matter which comes first. Suppose you already know E for some reason. Now, I want to warn you, we don't necessarily always know E first. That is, but suppose you say I know E because this band gap engineering gives a particular E. Well, it just says then P and dP dx is going to follow this relationship. All right? Okay. It may sound strange, but it's going to happen. Using Einstein's relationship, this ratio of dP to mu P is kT over Q. So we say electric field is equal to kT over Q 1 over P dP dx. All right? Okay? All right. Next. JC is equal to Jn. The collector current density is the electron current density. Electron current density is equal to Qn mu Ne plus Q dn dn dx. Okay? In this equation, we don't know what electron concentration is everywhere. In fact, we're going to find out what that is later on, at least in some special case. We don't know what electron concentration is. We're not assuming it's a linear function of x, as we often derive in some simpler model for bipolar transistor, right? So we're not saying we know what electron concentration profile is between emitter and the collector, all right? It's unknown. Okay? But we're going to bring in this electric field by using that relationship. All right, there's an electric field, whatever the electric field, all right, we're going to bring in here. Now here is where you're going to have to start make changes. If this is a silicon germanium model, then the electric field experienced by the hole is not the same as the electric field experienced by the electrons. Okay? All right? Okay? So you probably have to say this one, we'll call this one experience hole. I use this. Electric field experienced by the holes, let's say. All right, okay, maybe I'll do this. I'll just put this into this. The electric field experienced by the hole, all right, which is the gradient of this EV, all right. The electric field experienced by electrons, the gradient experienced by the EC. Is that right? All right. So I'll say the electric field experienced by the hole here. This E will be electric field experienced by the EN. Is that right? Right? And En would then be equal to EP plus DEG band gap dx. Is that right? And I guess has to be 1 over Q to get the units right. You see what I mean? In other words, electric field experienced by the hole is the slope of EV. We already have some of that. So what's the slope of the EC? Well, it must be that same slope as EV plus the gradient of the change of the gap between the two. Is that right? So assuming that you know this, because you're the engineer that designed that silicon germanium profile, suppose, right? Then you just add that into this equation and see what you can do. Yes? Brian.
Okay, I guess I have questions like, why is EC the one that's not flat? Because the band
Doesn't
gap
matter.
is more.
Mathematically, in this case, I'm not saying whichever is, if you look at this mathematics, it can be this and that. The relationship still holds. Whatever electric field experienced by the hole will be related to the electric field experienced by Yen in this manner. So mathematically, there's no problem.
Also, it's just I just don't really understand. It's like there's two different electric fields. What does that mean?
This is the same thing as when you have a built-in potential in a p-n junction, for example. You may have thought about this. What's the meaning of this built-in potential? Is this something you can measure? You cannot. You put a voltmeter there, you won't be able to measure that. All right? It's not there. However, as far as electron is concerned, it certainly sees a lower potential at one side, higher potential on one side, so it's going to move. Now, if we create a material situation by changing the band gap such that the potential for the holes are not changing, it's the same potential for the holes, right? Just because band gap here is larger, band gap is smaller. Certainly, the electrons will see a field. In other words, for example, this drift tendency must be balanced by a diffusion tendency. Otherwise, you have a net electron current flow. Here, you won't have that problem. You won't have a drift hole flowing. All right. So electron and holes can experience different electric field in the drift term, and what's responsible for the acceleration of the electrons is the gradient of the potential of electrons, and potential of electrons is EC. Potential of the holes is EV. To the extent EC and EV are not parallel to each other, electron holes will experience different electric fields. Okay. Does this lead to any inconsistency? It doesn't, fortunately. any place you look. Just like even though we cannot measure this voltage with ammeter, voltmeter, doesn't mean there's no electric field in between. That's because anytime you put any contact there, this differential eventually will give the complete loop a zero potential. You won't see any potential difference, okay? But like one junction, we'll see that. Similarly, this will not lead to any inconsistency. But one question that someone should have asked or could have asked, and we can interpret Brian's question as asking that question now somewhat belatedly, is in this, when I first introduced this picture to you, you could have asked me, why did I draw this way? You know, sure, the band gap is wider on the emitter side of the base and narrower on the collector side of the base, but why did I make the EV pretty flat and the EC is slow, rather than making EC pretty flat and EV is slow? Think about that answer while I take a new question from Turi and see if you can answer this. Why did I draw this? Or what is making the EV flat, and therefore all the change in the EG is reflected in the slope of the EC? Why is that? What causes that? All right? Turi, yeah.
I don't know, the question maybe is related to...
Sure. Reach over, get a microphone, please. Thank you.
So, but it seems like how the Fermi levels are set will determine which one...
That's
That
right.
was the question. Is that...
Doping, that's exactly right. You see, there's a relationship that is doping concentration determines the spacing between Fermi level and the EV, right? This p-type material. So as long as Fermi level is flat, that's the equilibrium case, and if the doping concentration is continuous, is constant, then EV pretty much is flat. Of course, you can in addition add a doping gradient if you wish. That's another matter. Now, once you have determined this slope of the Fermi level, I mean the EV, of course, you know the slope of the EC, assuming you know EG, right, at every point, right? So that's the same spirit here. So assuming we know DEG, DX, then there's a relationship between EN and EP, okay? So if you're interested, you can try to extend this, carry additional terms, see what you end up with, okay? All right. But right now, let's just ignore this additional term. This is it's given. I mean, it's not a known, fortunately. This is a given, right? We're assuming this is given. It's known, all right? So it doesn't complicate the equation much. But right now, let's ignore that. We'll just put the EP in here, substitute EN. Then this is what we get. Qn mu n times EN. EN will replace by this. Times KT over Q, 1 over P dP dx, right? We'll move here. The diffusion term we keep, Q dN, dN dx. All right. Okay, next. If you just collect the terms, all right, and take my words for it, there's no new physics. We really just only collected the terms. We didn't do anything from the previous slide. You end up with Jn equal to Q, KT over Q times mu n. You take that out in front. All right? If it's not so clear, let me do take this back a little bit here like that. And so what we did is we take the Q out. They both have Q. They have KT over Q and mu n. You got that, no problem. You ask, hey, what about here? Well, do you remember Einstein's relationship? dN is equal to KT over Q times mu n. Is that right? Okay, so take that out. All right. Then you also take out I guess you don't take out anything else. So what you have here is N over P dP dx, right? N over P dP dx, N over P dP dx, right? And here you have dN dx, dN dx. Okay? All right. So we just collected terms and end up with this new equation. Just by observation, just by looking at this, you notice it can be rewritten as 1 over P times d Pn dx. It's easy to verify that just by differentiating this and verify it's the same as that. For example, when you differentiate dPn dx, what do you get? You get P dN dx plus N dP dx. Is that right? Yeah? The first term divided by this P here give you dN dx. The second term, sorry, just dx. The second term, if you divide by this P here, you get N over P dP dx. Is that right? Okay, so again, the This is fine. Now we can do some integration. You just integrate left and right hand side with respect to x, and you also, excuse me, move some terms to the left hand side. It's easier. So what do we move to the left hand side? Left hand side already had the Jn. We also moved the Q to the left hand side. We moved the Dn to the left hand side. We moved the whole concentration P to the left hand side. That's that. What's left on the right hand side is this quantity, and it's here. Is that right? Okay. Do you see this equation can be rewritten this way? All right. Now, why did we keep the diffusion constant in the inside integral? Just in case we want to keep the mathematics as general as possible, we can say, hey, even the diffusion coefficient may be changing, right, as function of x, because the doping concentration is different or something like that. All right? And certainly the whole concentration may be changing, and this could change because of doping, and later we will see there are reasons the whole concentration can change, even if I have uniform doping. All right? This can happen. We'll see a case later on. And on the right-hand side, we have dpn dx. Of course, this is very easy to see. This cancels out. dx cancels out. We just integrate dpn. It's very easy, right? Okay, so let's carry out the right-hand side integration first. We'll keep the left-hand side the way it is. Carry on the right-hand side. Right-hand side simply becomes pn, evaluated once at w, one at x. Is that right? Is that correct? Yeah? All right. Now remember, it's interesting that the two limits of integration, we're choosing between w and a point in between 0 and w called that x. We're not integrating from 0 to w, all right? Remember that. And you will see why we do it that way. We're integrating from x to w. So then we get pn evaluated at w minus pn evaluated at x. So p at w, n at w, minus p at x, and n at x. Is that right? Now p at w and n at w is easy to do. This just tells us what's the pn product at the edge of the reverse biased pn junction. Now I will not explain this to you, but just to just maybe just assume you already know this. At a PN junction, when there's a bias across PN junction, there's a boundary condition. Some of you may know it as the quasi-equilibrium boundary condition. Others may know it as simply as the Shockley boundary condition. At the edge of a PN junction, the PN product is equal to Ni squared exponential QV over KT. Okay, this is why the minority carrier concentration increase in proportion to exponential QV over KT, because we usually assume the majority carrier concentration is independent of bias. Here we did not even make that assumption. In high-level injection, both can change. All right, but the basic boundary condition is that PN product is equal to Ni squared exponential QV over KT. That's a fundamental boundary condition called the quasi-equilibrium boundary condition. All right, and then minus P at x and N at x. Okay. Now let's further simplify this by saying it's a normal bias. The emitter base junction is a reverse bias. This V is a negative number. It's a reverse bias. At reverse bias, this term just drops out, go to 0, right? At edge of the reverse bias junction, PN product is very small. Okay? Just minus Px and x. Now, what have we accomplished? Why do we do this? What we have done, we have derived expression for the electron profile. Remember, if we had a uniform doping, we don't have any drift field, the solution is that N, electron concentration as function of x, is a triangular shape. Remember that? That's what you remember probably from the PN junction theory, right? Here we found a new equation. N as function x is not a linear function of x, but rather it's this. It's not that difficult to see. I mean, it may be difficult to evaluate numerically, but if it's a computer, it's really trivial to do. All you need to do is, if you knew the doping profile, P as function of x, yes? Yeah? P as function appears twice, once here, once inside the integration. And you can numerically integrate that, no problem, right? If you know P as function of x, you certainly integrate how much there is between x and w. Is that right? Just look at this function a little bit. If for some reason you knew P as function of X, if you knew that, right? Suppose that's given. Can you see that right-hand side can be evaluated? All right? All right? Okay. Would be really interesting, fun for you to try to, make some arbitrary, simple assumption profile for PSX. For example, linear dopant profile. See what you think you get for an N profile. All right? Let me see if I have a special case to show you. It's okay, I don't. So maybe I just take one moment to show you a trivial case. A trivial case is PSX is a constant, uniform doping. First, if it's uniform doping, without evaluating right-hand side, do you already know the answer to the left-hand side? What is the electron concentration profile if the base doping is constant? It's linear, right? It's like that. Is that right? So let's quickly verify if that's the case. If this is not a function of X, this is no longer a function of X, right? This term. So here is constant, not a function of X. Constant, you integrate it with X, what do you get? It's a linear function of X, right? That's what you get. Okay. But with any arbitrary doping profile, you will be able to get that. If you had carried a constant term earlier, or some known term earlier, why don't you try that? What term you will get? All right, you will, can just know the what the doping the carrier concentration profile is. Now, why do we want to know the carrier concentration profile? It's more than just academic, because carrier concentration profile is intimately related to speed. All right, but before I get to the speed, I'm going to look at the special case of this equation, and then I'll bring this to speed later. Show how this is related to speed. All right. The special case is the following. I use special case. Suppose I evaluate that at x equal to 0. If it's at x equal to 0, right the base emitter junction edge, do I know the minority carrier concentration at the edge of the PN junction? Yes, we do, because it's equal to n naught exponential QVBE over KT. That's the boundary condition we just reviewed earlier. Is that right? All right? How about right-hand side? Of course we do. We just now have to do this integral all the way from 0 to W, that's all. Right? Assuming P as function X is known. Right? So then the equation can be rewritten in such a way we put JC on the left-hand side. Put JC on the left-hand side, right? So this exponential QVB over KT will be on the right-hand side. So what do we have expression for the current density of a bipolar transistor? And many of you have seen this before, I'm sure. So what we have then expression of the collector current as function of VBE. It's exponential function of VBE, as we saw in the previous slides. But what the previous slide did for us, it gave us the term in front of the exponential term. It's this. It's equal to QNI squared over 0W dPx dx, QVBE over KT. Do you follow that? Right? Okay. I'll leave this as a question for the reader. Proof, if you will, if Ni is not a constant, but rather a function of X, such as in the silicon germanium case. All right? All right? Turns out what you should do is to take that out and put Ni squared here. So again, if you know the silicon germanium content as function of X, then you already know Ni as function of X, then you will be able to predict what the current is. All right? This current will tell you, for example, for given VBE, just because silicon germanium has lower bandwidth and therefore larger Ni square, you will get more collector current. Is that right? You get more collector current. Yes? Yes? Right? That's why you have a larger current gain. Because for same VBE, the whole current injected into the emitter is not changed by the silicon germanium base. And yet the collector current is increased by the use of silicon germanium base. The whole injection into the emitter is not changed, not affected by that. And therefore, you end up with larger current gain, right? So silicon germanium is good for that. Okay? All right. So, very often we define a quantity, put those things in the numerator, still numerator, all this integral put in the denominator, we call Gamow number, all right? And there's a lot of debate whether you should include the D in the Gamow number or not. Some people only put a P in the Gamow number definition. Others put a D in there because it's so easy to include that mathematically. And you know, it really be great to generalize your concept of Gamow number by including Ni there. That way you can deal with silicon germanium band gap also. All right. So it's just up to you to define what Gamow number is. Some textbooks, some only put Q, P there. Some insist on, well, doesn't matter. Some put D there. Some put some electronic charging there. But actually, Ni today should really be put in there. All right. That would be a more general definition of Gamow number. Okay. All right. And in fact, I love that. And in fact, why don't I just do this? I'll take this out. All right. You see, this is prepared before I talked about silicon germanium transistor, right? Talk silicon transistor, we should not consider Ni here. Ni has to be included in here. It may be a function of X, so it should be part of the Gamow number. Okay. So let me just finish stop there about this. So Gamow number is an important quantity in bipolar transistor. All right, I'll say more about Gamow number. Gamow number is important. And we often make a plot called a Gamow plot. And this Gamow plot will plot the log of collector current versus base emitter voltage. What you expect is a straight line, right? Because exponential function of VBE, right? What can you say about the slope of this straight line? What can you say? Forget about this part, all right? You get a straight line, and what can you say about this the slope of the straight line? 60 millivolt per decade, so thank you very much, right? So anytime you have this QV over KT relationship, exponential QV over KT relationship, 60 millivolt per decade, all right? That's what you can expect. Very similar analysis can be done to show that the whole current injected into the emitter from the base injected in the emitter, we call this base current. Base current, which flows into the emitter, that base current is also equal to QNI over G Q VBE over KT. And we will call this GE the emitter Gamow number. So I have a base Gamow number, QGB, and emitter Gamow number, GE. Right? I can add NI here as well. Right? This will be more general. NI square, I'm sorry. NI square. More general. So this will be the emitter Gamow number. And if you plot IB versus VBE, you get a second straight line. Same slope, second straight line. Right? The ratio of these two lines, the two curves, of course, is beta. Right? In other words, you want IB to be small. The two curves have same slope, but you want the magnitude of IB to be small. How can you do that? You just have to make sure there's a lot of electrons in the emitter, meaning dope the emitter heavily. All right? Or you have a very small number of intrinsic carrier concentration in the emitter. In other words, you sell large band gap material in the emitter. Okay? Now, for example, if you are using gallium arsenide, transistor today for RF applications, for RF power amplifier, for example, what you will find is the base is made of gallium arsenide, and the emitter is made of material with even larger band gap than gallium arsenide, such as gallium phosphide, gallium aluminum arsenide. Okay? And anytime when the base and emitter material are different, we use a name, heterojunction bipolar transistor, or HBT. Heterojunction bipolar transistor, yeah, HBT. Yeah, I don't think people call it HJBT, HBT. heterojunction bipolar transistor. That means the emitter base junction is made of two different materials, right? Heterojunction. All right, so that's the concept of the terminology, Gummel number, and this plot as a Gummel plot, all right? We will not get into why this curve tends to bend, all right? And the current gain is simply equal to the ratio of collector current and base current. Therefore, it's simply equal to the ratio of the two Gummel numbers, emitter Gummel number and base Gummel number. So use this terminology, then the discussion of the gain is simplified. You just want large Gummel number for the emitter, you want small Gummel number for the base. Right? Okay. Any questions? I know this is a collection of several different topics, so it's probably somewhat confusing and difficult to follow. If you have any questions, please just raise your hand. All right, next. Now here we talk about speed now, and we're going to pick up on the trend that we put away a little earlier. Just what determines the speed of a transistor? You all heard about the term transit time. You probably also heard the term stored charge. These two things are very tightly related to each other. All right. Stored charges means the following. You have an MOS transistor. Bipolar transistor, N, P, N here. You bias sufficiently so that a given amount of current flows through the collector. Let's say 1 milliamp of collector current, right? Right? The question is, in order to support this 1 milliampere of current, how much minority carriers will have to be stored in the space in order to support this 1 milliamp of current? If you have to store a lot of carrier in the base to support this 1 milliamp, you have a slow device. If you store very few minority carriers here to support this 1 milliamp, you have a very fast device. How does this relate to something we talked about so far? It's related to doping. It's related to electron profile. We already said if this is a uniform doped base, or you will have the electron concentration is going to have a linear profile in it. The only thing you can do to support a particular collector current, let's say larger collector current, is just to put in more electrons in it, so you get the larger slope until you reach that current, right? So clearly you can see the stored charge is linearly proportional to the current, right? And the ratio, by the way, between the stored charge and the current is the speed. Maybe that's a quantity. I'll go to this equation first. If you know the stored charge, you divide that by the current, you get the speed, the transit time speed. How do you understand that? Well, this is the way to understand that, really. Suppose you can somehow magically suddenly cut off the injection from the input. Input is the emitter side is input. Is that right? You can suddenly cut off that injection from input infinitely fast. Will the collector current suddenly stop? It won't stop until it drains away the electron stored in the base. Is that right? How much time would it take that to drain away? Isn't that the stored charge divided by the current? Isn't that right? The charge divided by current gives you a time, right? And actually you can prove this more formally, more rigorously, that that's exactly equal. The transit time is exactly equal to that, all right? Okay. Therefore, if you want a fast transistor, you want to minimize stored charge. So if there's a way, just by different doping profile or different band gap engineering in the base, we can create a situation that this much of current can be supported by this kind of electron profile. It does not even have to be linear. I don't really know what kind of shape it is. Then you have a very fast speed. Is that right? Is that right? So the question is, what is the charge stored in the transistor? Well, of course, charge stored in the base at least is equal to the electron concentration in the base integrated from 0 to W. Is that right? Yes? And earlier we have expression for this NX. It's this expression you may not remember, but we derived the expression for NX, right? We said if we knew P as function of X, we would know N as function of X. A special case is uniform hole concentration, then we'll get the linear profile for electrons, right? So we just take this, put that in this equation for the stored charge, and we get this. It's not even a function of the base bias, emitter base bias, because both the stored charge and the collector current are exponential functions of QVB over KT. I've seen that. So that drops off. So this is a general expression for, Q and Q would also cancel out, by the way. I don't know why I'm carrying this, because both these two terms have a Q in front. So they also cancel out, all right? Okay, so we'll just take this away. So that's expression for the transit time, all right? And if you have a, if the Ni is a variable, then Ni would not Ni squared would not cancel out. Right now, Ni squared canceled out because we're assuming the band gap is uniform in the base. If band gap is not uniform in the base, you will see that a graded band gap will be beneficial to us to this transit time. All right. I wish I had time to give you another homework set. It would be wonderful homework to work all this out for a silicon germanium transistor. All right. Okay, so this is the way to relate arbitrary doping profile to the transit time. Okay, let me tell you that just by using proper doping profile in the base, you could cut down this by about order of magnitude. All right. The unfortunate thing is this effect doesn't work so well when you start having band gap narrowing. When you have to dope some portion of the base so heavily that start have band gap narrowing, then start have problem. All right. I'll give you a special case, just for fun. We saw a special case earlier for the electron profile. Now let's look special case for the transit time, shall we? Special case for transit time. Again, we use the constant, the base doping as special case. Constant, all right? Constant base doping. So let's first do this integration, the first integral, okay? This part. P is just the doping concentration, and B. Right? dn dx prime, right? From x to w. So you get mb over dw minus x. Do you agree? This is what you get when you integrate x prime from x to w, you get w minus x. All right? Next, you put this into this outside integral, right? You get 0 to, this time not from x to w, 1 to 0 to w, right? 1 to 0 to w, right? From 0 to w, because I'm looking outside integral now. 1 over dn, that comes from here, 1 over dn. Oh, there should be a mb, of course. Let's see, where does mb go? Oh yeah, mb cancels out. This is mb. I guess I took one step faster, because this is mb, is that right? Right? So this mb cancels out that mb in the numerator. This came from that term mb, this is this mb canceled out. So there's no mb here. All we have is the dn, so we have 1 over dn. We have w minus x, and then we integrate with respect to dx. So what do we get there? We get 1 over dn, wx minus x squared over 2. Take my word for it. You end up with w squared over 2dn. Now, some of you may remember that is what the uniform base transit time is. Okay? This is a simple trivial case for using these. So if you have any other kind of doping profile, you'll be able to estimate what that transit time would be. Okay? All right. Next, I'll cover this a little bit and just ask you this question. All right? So we have now a theory to estimate the profile of the minority carriers in the base for arbitrary doping profile, right? May not be linear. We now have an equation that allows us to calculate the transit time for arbitrary doping profile. Can we also come up with some understanding of how the base transport factor depends on this arbitrary doping profile? Okay? Let me remind you what base transport factor is. If this is the first time you see the term base transport factor, you may not be able to follow what I'm going to say. Don't worry about that. But if you know what base transport factor, I'd like to just go through this the thinking process with you, all right? What is base transport factor? Base transport factor is the ratio of the electrons that arrive at the collector to the electrons that are injected into the base. For example, if 100 electrons are injected into the base, 99 of them survive the recombination and reach the collector, then base transport factor will be equal to 0.99. Do you follow that? If 100 electrons are injected from the emitter into the base and only 90 of them reach the collector, the base transport factor is equal to 0.9. All right? So base transport factor just means the fraction that hasn't died from recombination. All right? Knowing this is the case, there's a very easy way to extend what we have done so far on this page to give an equation that will allow us to predict the base transport factor for arbitrary doping concentration. It does involve one new concept. I think most of you studied the base transport factor by trying to solve some current density at the emitter side, current density at the collector side, take the ratio. But you shouldn't be thinking about things like that all the time. Usually it's better to think at higher level. At higher level as possible. If you just think the base transport factor, meaning the fraction of the electrons that have not suffered recombination, if you just use that statement, the fraction of electrons that have not suffered the recombination during its transit through the base, then answer, the mathematical representation of that statement is exponential minus tau transit time over tau n, the recombination lifetime. I'd like you to think a little bit about that. What does that mean? What is the meaning of recombination lifetime? If I all of a sudden introduce 100 excess carriers into a piece of silicon, and if I know the recombination lifetime is 1 microsecond, does this mean that all these 100 carriers will live, no one is lost by recombination up till 1 microsecond, and that moment, all of them on cue suddenly recombine and die? Is that the meaning of recombination lifetime? What do you have as meaning of recombination time in your mind? It's a stochastic process, right? That is, immediately some start to recombine, and many of them will live long before 1 microsecond, right? So exactly mathematically, how does this 1 microsecond factor into the life of these 100 electrons? What it is that this much will remain. At any time t, this much will remain. T over 1 microsecond will remain, right? That's the random process. So stochastic process, if you know they're random and they have a mean lifetime of 1 microsecond, that's the meaning of it. Is that right? The fraction that remains is exponential minus t over 1 microsecond, right? Since we know it takes tau tr microseconds to transit through the base, and that is what I meant as the link to arbitrary dopant. So if you know the arbitrary doping profile, you know the transit time is tau tr, then what fraction can survive that transit? It's exponential minus tau tr over tau n. Following what I'm saying? Is that right? So this is the expression for the model for the base transit factor for arbitrary doping profile. Okay? Okay? And some textbooks actually have tried to derive this using drift diffusion, and end up with a very long expression, which is only a poor approximation to something like this. So you don't need to do that. If you know the transit time, you can easily predict the transport factor just by looking at that. Again, looking at special case, just for fun. Very special case, all right? Well, I won't bother with that. Okay. You probably have in mind some special expression for the base transit time for the uniform doping case. Many textbooks give you that, right? Obviously, it's not an exponential term. But just try to see if what you have is equal to this. You see what this is? This is approximation to this. It's Taylor expansion of the exponential term, it's this. And if you substitute the special case of tau transport factor you will end up with the usual, first course model for the base transport factor. All right. Okay, so those are some ways to deal with the concepts you probably have already heard before, but we just generalize them for you. All right. All right. The last topic, couple of slides, 2 slides, I believe, that I think I like to discuss with you is the BJT breakdown voltage. This is something we already made use of in the discussion of the snapback breakdown of MOS transistor, right? Okay. At that time, I just asked you to believe me. There are 2 breakdown voltages, the BJT and that, all right? And many of you actually had questions about that. You came to my office hour asking about snapback. So clearly, it's not a straightforward thing to see why you should have this 2 breakdown voltages. So these 2 slides will talk about those 2 breakdown voltages. The first one is the easy one, called the base collector junction breakdown voltage. That means, suppose I just leave the emitter open. I put a electrode to the base, electrode to the collector, reverse bias it. At some point, this base collector junction will break down. Is that right? That's known as VBCEO, the usual base collector breakdown voltage. You just apply reverse bias between base and collector. Okay? So there's nothing more to say about it, just our usual PN junction breakdown. All right? That's the larger of the 2 breakdown voltages. What's the second breakdown voltage? A second breakdown voltage is we leave the base open. We apply a bias between emitter and collector, and still using the same the polarity such that the base collector junction is reverse biased. Namely, the collector is more positive. If the collector is more positive, if the emitter is ground or more negative, you notice this NP junction will be reverse biased. Is that right? Right? If we put positive voltage here, this NP junction will be reverse biased. That's the one's blocking current, right? If anything, the base emitter junction will be forward biased, right? You either say it's unbiased or forward biased. Any forward current flowing through it will cause this to be slightly forward biased. Is that right? The base collector junction is reverse biased. So under this condition, you say, well, the breakdown voltage should be the same, because still the voltage is being blocked by this base collector junction, right? The base emitter junction is not blocking any voltage. Is that right? Now in reality, it's not. If you do this measurement, you're going to find this structure will break down a significantly lower voltage than the first case. Okay, often by a factor of 2 or even 3 or even more. All right, so why? That's what we're going to be talking about. All right? So we model this way. Even though base is floating, right? It does not mean there's no supply of base current. In other words, it doesn't mean there's no hose that's supplied into the base. There is. Because if there's impact ionization at this base collector junction, just because it's still reverse biased, right? Right? There's impact ionization. If there's impact ionization, what happens? Electron hole pairs are created, right? Electrons will be swept into the collector, no problem. Holes will be swept into the base. That becomes supply of base. Holes, right? So the whole current, it's a whole current now. It's generated internally, whole current. That whole current is the hole due to impact ionization. Now, how many holes are created by impact ionization? It's equal to the emitter current times m minus 1. Let me explain what they are. Emitter current tells us how many electrons flows from the emitter through this reverse bias PN junction. Is that right? That's emitter current. M is known as multiplication factor at the base collector junction. Base collector junction is reverse biased at some high field. Because it's high field, if 1 electron going in, on average, maybe 1.1 electron will come out because this 10% of chance will create impact ionization. If that's the case, then the multiplication factor is equal to 1.1. All right? If the multiplication factor is equal to 2.3, that just means 1 electron going in, 1.3 additional electron hole pairs are created, therefore 2.3 electron go out. In that case, m is equal to 2.3. So m minus 1 times the electron going in is the number of holes that are created. All right? Okay? All right. So m minus 1 times the electrons going in give us the hole that's created. Why do we even bother talking about multiplication factor? Just because in the literature for many years, just through the early days, people studying p-n junction, there has been an empirical sort of a model for the multiplication factor. That is, if one electron goes into a p-n junction, how many come out? This, for example, is used in an avalanche photodiode. In order to get a more sensitive photodetector, what we can do is we actually shine light not just on any p-n junction to create electron hole pairs, then we can collect that photocurrent. It works. We actually shine light on or near a p-n junction biased at high field, such that if the light, one photon comes in, it creates one electron hole pairs. This electron, let's say, diffuse to the edge, gets swept through the high field region. When it came out, it's not one electron came out, 3 electrons came out. Now you get a more sensitive photodiode, right? It's called an avalanche photodiode. So people have been studying this multiplication factor for many, many years. And empirically, it's known that the multiplication factor can be expressed in this manner. Okay? That is, multiplication factor as function applied voltage goes like this. Clearly, at the point where p-n junction voltage itself breaks down, this is the p-n junction breakdown voltage, not the transistor breakdown voltage, is the higher one, the junction cell, all right? At the time junction cell breakdown, the multiplication factor is infinity. That's almost by definition breakdown, such that if there's any, thermal generation, one electron junction just breaks down, right? Okay. But what if you apply a voltage slightly smaller than that? Well, it turns out the multiplication is a little smaller, not infinity. What if you apply a voltage even smaller, then the multiplication factor is even smaller, right? So so if this is infinity, 10 may be here. So the avalanche photodiode may be biased here, for example, right? Okay, so empirically, when people look at this data, it can be expressed in this manner. It's 1 over 1 minus V, the applied voltage, over the breakdown voltage to the m's power. Okay, first don't worry about m's power. Just say 1 over V over VBC, breakdown voltage. Now clearly, when the voltage is equal to the breakdown voltage, the the denominator becomes 0, and this multiplication factor is infinity, right? That's what we expect. When V is equal to breakdown voltage, you have infinity multiplication factor. When it's smaller than breakdown voltage, then it's less than infinity. So what does M does? Actually, M determines the sharpness. If we make M equal to 1, this curve is not sharp enough to fit the data. M equal to 2 will be sharper. M to 3 could be even sharper. If you make M equal to infinity, it becomes just a right-angle curve. See what I'm saying? All right, that's what this function is. So empirically, M equal to 3 seems to be common. All right? All right. This is just empirical fit, right? Some case maybe 4, and it's hard to say. There's no theory that should be 3. Just fitting like 3. All right. With this in mind, now we can write down some equations. Let's give us a review of bipolar transistor relationship. For bipolar transistor, in this case, because base is open, the collector current is equal to the emitter current. Is that right? Collector are equal. There's no base current, no external base current. So collector current and emitter current are equal, right? And emitter current is always equal to beta times IB, right? Plus some leakage current is very small. You will see why we want to keep it, plus some leakage current, right? So emitter current is equal to beta times IB. Is that okay? Is that right? And yet, IB is equal to, we call this IE here. I changed to IC. I don't really know why. It doesn't really matter. All right, let's call IE, IC roughly the same. They don't differ very much. All right. Okay. IC times M minus 1 plus I over leakage current. Right. IB is equal to IC M minus 1. Call that approximation. IE, IC we're using interchangeably. IC M minus 1. Okay. All right. So far. All right. Next, we'll combine terms. Combine these two terms with IC. So IC 1 is the left-hand side, is a 1. Move this IC term on the right-hand side to the left-hand side, becomes minus beta m minus 1. Is that right? Equals leakage current. Now you see why I want the leakage current. I don't want a 0. I want to keep that a little bit. What next we'll do is I'll keep IC on the left-hand side, divide this parenthesis to the right-hand side. All right? Okay. And that's the last slide now. This is it. IC is equal to some leakage current, very small quantity, divided by 1 minus beta m minus 1. All right? Now, before we go on more, does m have to be equal to infinity in order for IC to become infinity? IC infinity meaning breakdown of the transistor, right? Does m have to be infinity before IC is equal to infinity? No, it doesn't. Actually, m, well, why don't I just, I'll give you the answer. In fact, if m is only equal to 1.1, that's probably enough. If m equal to 1.1, 1.1 minus 1 is what? 0.1. 0.1 minus beta is a pretty large number. If beta is 10 or larger, if beta is 10, we already have 1. 1 minus 1 gives me infinity, right? So earlier you have seen 1.1 m is not even close to breakdown, right? We just have a little bit of impedance, right? M equal to 10 is where we operate as a photodiode. M equal to infinity is junction breakdown, right? Here, m equal to 1.1 is enough to cause the current to go to infinity, right? So this is the main reason why when the base is open or when the emitter base is forward biased mainly, then we have a much lower breakdown voltage, all right? Okay, but before we close the loop, let's just finish the mathematics a little bit, because I even gave you some square root of relationship. Let's just quickly finish that, and you don't have to follow this through very much. I won't bother you with either. First, we replace m with that relationship, which have to do with V and the junction breakdown voltage and M, right? And then after a few mathematical manipulation and simplification, I end up to be this relationship, okay? That is, in order for IC to become infinity, the denominator has to be 0. In other words, this quantity has to be equal to 0. This quantity has to be 0. I put here, all right? Finally, since the last step, why don't we do it together? So you feel that you have seen how this came about. At this point, what we do is we put the beta on the right-hand side, okay? Put everything else on the left-hand side, and that's what we have, okay? In other words, we just multiply this whole thing. First, let's put a 1 to this side, okay, to the right-hand side. Then multiply the denominator to the right-hand side. So this is what we get, okay? This is what we get. So the question is, at what kind of voltage do we have to apply? Okay, by the way, when this is 0, that voltage, okay, when this is 0, that particular voltage is what we call VCEO. That's the breakdown voltage between collector and emitter, right? Right? When this is 0, when the voltage is large enough for this denominator to be 0, that voltage is the collector to emitter breakdown voltage, right? Okay, so now we can see we have a way to get collector to emitter breakdown voltage and base collector junction breakdown voltage raised to the m, that ratio raised to the m, minus 1 equal to beta. So finally, the very last step, we want expression for this. So this is equal to VBCEO mth root of beta plus 1. You see, beta plus 1 to that side, take the mth root. That. You see that? All right? Okay. Now, m, we said it's about 3. Whether it's 3 or not, it's hard to say. About 3. Beta plus 1, often we don't even want to carry the plus 1, just say beta. So if beta is 100, you take the third root, you will end up with something like, pretty large number. Okay, but usually beta is not quite 100 because breakdown happens when the current is still not very large. 1 microamp maybe it's already breakdown. 1 microamp beta might have not reached the peak value, might have actually. So therefore, the transistor breakdown voltage is significantly lower than the base collector junction breakdown voltage. Question?
Actually, there's two. So the first one would be, I take it this beta is AC beta, so that if the higher frequency you go, the less this effect.
Actually, I am thinking of DC beta. I'm still considering the whole thing is happening very slowly, right? You're ramping up the VCE and see at what point you get a snapback. So it's really DC beta.
But wouldn't this be valid? This equation should hold. There's no frequency dependence. I mean, the beta.
At this point, there's no frequency dependence.
Okay, so that means if you had some sinusoidal excitation, then we go to beta j omega. That's the first question. The next question was, you assumed the base was open, and it would seem like then if you shorted the base, you would get better improvement. But I have an add-on to that.
Right.
It seems like that doesn't really happen in practice as much as looking at this would tell us. Can you say why?
So therefore, I want to now move the discussion to MOS transistor, all right? You're probably thinking about bipolar, but for the benefit rest of the lecture, the class, I want to answer your question by framing it in the case of MOS transistor, all right? So now let's look at MOS now. We ground this, right? We ground the collector, let's call the source, right? And we can even ground the gate just for the sake of it doesn't matter. We even ground the base, right? The body, which is our base, right? Yes. And we're ramping up this drain voltage VD, right? Right. And we want to find out at what point when this NPN bipolar transistor will break down. I'll phrase it this way. We want to know at what point will this NPN transistor break down. Is that right? We want to know the breakdown voltage NPN transistor. The question is, in this NPN transistor case, is the base open or is the base shorted? Right? If the base and emitter are shorted, of course, we don't have that amplification. You don't have any beta, right? There's no bipolar transistor action. If it's open, then you have the bipolar transaction. So in this case, is the base bipolar transistor operating or not? Do we have a transistor gain? Do we have bipolar transistor gain? And that's the question. I know you already anticipate a complicated answer, but the simple answer is you should first say, if you say, yeah, this should give us the higher of the breakdown voltages, is the correct answer, right? Because when the base and the emitter are shorted together, you should get a higher of the breakdown voltage. When does that answer become not valid? Well, that's when you consider there actually is some resistance in the substrate, such that when current starts to flow, we now have an IR drop that's equal to I sub times R sub. If the I sub is large enough, even though the body is grounded and the source is grounded, these 2 points of PN junction is not short to each other. If this difference is as large as 0.6 volts, then we know the bipolar transistor is on. When the transistor is on, it's just like opening the base. It's on, right? Right? It's on. So transistor will have the gain, and therefore the breakdown voltage suddenly drops into the lower value. All right. So that's what it is. So if you just take a so that's what happens. So when you now look at MOS transistor now, MOS transistor, ID versus VD, you're ramping things up to this point. You know, all to this point, R sub times I sub is less than 0.6 volt. So there's absolutely no problem. All right. Waiting in the wing somewhere is a vertical line. You should think is this point. Let's say, this point is what we call the VCEO, or lower of the two breakdown voltage of bipolar transistor. We can cross that no problem because the base is grounded, base is shorted. No problem. Up to this point, unfortunately, now any additional current created here, they're not going to be shunted. So maybe some of you may find the circuit equilibrium circuit, not equivalent circuit may be helpful. So what we're saying is this: we do have a current, base current created, just we said, due to the impact ionization, right? We'll create this base current, but we are shorting it out into the substrate. It's this one. Shorting it out into the body contact. Is that right? So as long as this impedalization current is being drained away by the body contact, this bipolar transistor does not have any gain. Agreed? Right? But why should the impedalizing current prefer to go through this path rather than go through this path? If it goes through the second path, we're in trouble. But why should it prefer go through the first path rather than the second path? Well, of course, simply because this is lower impedance than that transistor, right? That junction. But do you remember that the impedance of a forward biased junction drops precipitously, exponentially with increasing forward bias? Remember the G of the diode, right? What is the impedance of a diode? Right. And it's not beta Z-Y. Actually, it's equal to I divided by KT over Q. All right. This is admittance. I'm sorry. Admittance equal I divided by KT over Q. All right. So when I is large, this becomes large. Okay. In other words, when it's forward bias, the impedance current will no longer favor to go this way. Will go this way. This actually is lower impedance than that path. If you say, that's not possible, then how about pushing even more currents through this? Make this forward bias to 0.7 volt. Okay, this becomes the path for all the current to flow. That's why you start having large gain. Okay? So when I say 0.6, I just give you a number. It could be 0.7. 0.8 doesn't matter because the substrate current increases with VD so rapidly, a factor of, whether it's 0.6 ratio to 0.7, doesn't matter. All right. So we can pass through that no problem because at this point, the impedance current is flowing through this. At this point, however, the junction is forward biased. Now, the PN junction becomes the favored path for any impedance current. Right? So your feedback gain start to increase. You suddenly just drop back to this. So this is called a snapback, right? Okay. So this is the theory for the bipolar transistor breakdown voltage. All right? Okay, other questions? All right. Tori, did that answer the original question you wanted to ask about bipolar transistor? Okay, let me rephrase this and answer it. Tori was asking, now go back to bipolar, not MOS. He happens to know that even if he truly ground the base, all right? He truly ground that base terminal. He measured the breakdown voltage. It doesn't differ that much. It's a little higher than keeping it open, but not that much higher. Is that what you're going to ask? All right? Not what I said, factor of 3 or factor of 2. So how do you answer that? How about some of you try to answer that? Why is it? The hint is that think about this. The same situation as here. In other words, when you ground, is that really ground? That's the question. If you think that, now think about the cross-section of the bipolar transistor. Think about cross-section bipolar transistor. Now, when you ground the bipolar transistor base, do you truly ground the bipolar transistor base? Here already says this resistance of the base is causing this problem. We cannot truly ground the base, right? Now think about the resistance of the base of a bipolar transistor. That's why I say think about the cross-section of the bipolar transistor. And think about the resistance value of the base of that transistor. Base is very thin, right? Very, very thin, right? And you're making contact to the edge of the base. What about in the middle of the base? Are you really grounding it? Middle meaning in the middle of the emitter, are you grounding it? Can you possibly ground it? Right? And that's the reason. So we're talking about theory, practice, and you don't see that big a difference. All right? But there's difference. Okay? There's a difference. I don't think there's no difference. Okay? All right. Other questions? Okay, then thanks very much for joining me in this course this semester. I really enjoyed it. All right? Thank you. Bye-bye. I have the urge to stand up taking a bow. I don't know how many of you have taken a flight on the airline called EVA. It's experience. You should try that.